Okay, so we're in section 3.3, arc length and curvature. So we're going to determine the length of a particle's path in space by using arc length function. Explain the meaning of the curvature of a curve in space and state its formula, and describe the meaning of the normal and binormal vectors of a curve in space. So we're going to just start off with a simple curve. So if you remember, we had something that looks like this. And then we have this curve that's doing its thing like that. And we describe how this curve propagates as such. So this is at some time, and then this is at a later time. It will move to here, and then at a later time, it will move to here. And so each one of these vectors are R of t, and R of t gives us the position or the location. I think that one, for some odd reason, let's undo that one, because that one didn't have a vector. I want a vector. Okay, there we go. All right, so what we'd like to do now is we'd like to find the length of a curve. Okay, so in order to find the length of a curve, we're going to start off at some t equals a to some t equals b. So we're going to talk about the arc length. Calling that L, along a smooth curve. Remember, a smooth curve has no kinks or cusps. Okay, with position vector R of t, and this is f of ti. If you remember, x is equal to f of t plus g of tj. Y is equal to g of t plus h of tk. Z is equal to h of t. So if you remember, this is just as a vector, x of t, y of t, and z of t. All right, from the point R of A to the point R of B, where A is less than or equal to T is less than or equal to B is. Finally, we get there. Okay, so L, let me move this. Going to need the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. We're going to integrate that thing from a to b dt. So if this point right here happens to be R of A, and this point right here happens to be R of B, we are talking about the length of the curve from here all the way to there. Okay. All right. Another way of writing this is the square integral from A to B. Again, big square root we can write it as x prime of t squared plus y prime of t squared plus z prime of t squared dt. Now you have to remember x and y, if it only has an x and a y, it's going around in the plane. But if it has a z component, then it's rising in the air as well. Okay, so we already know now that nu of t, so let's just recall for a moment. Nu of t, that's the speed. Well, it's simply just this thing inside. This is nu. So nu of t is simply just that thing. Okay, so that's nu of t. All right. And if you remember, that is also, we can write it as the length of the velocity vector, or we can write it as the length of r prime of t. So all of those are the same. It's nu, it's the length of the velocity vector or the length of the derivative of the position vector. It can be written all as such. Okay, so our first problem is find the arc length of one turn and that one turn is from t equal to 0 to t equal to 2 pi over omega of the helix with parametric equations x of t is a cosine of omega t. Y of t, that's not y prime, let me be clear. Y of t is equal to a sine of omega t. And z of t is equal to b times t. Okay, so I want to just draw this for a quick moment. Okay, so as you can see, in the XY coordinate system, this is going around in a circle. So it's actually going around in a circle of radius a. Okay, the difference is as t grows, so does z. Okay, so this particular curve starts right here. All right, so when t is equal to 0, this thing is, you get r of t is a 0, 0. So it starts off right there. But it follows this circle curve. So it's following this curve, but it's increasing. So when it comes back around to here, it's actually at a higher z. So it's going around at that same curve, but each z brings it up in the air further. So it's still going around that same circle, but each Z brings it up. So now what we want is one full turn of this thing to where it comes back around to this point, but now it's up in the air, okay? All right, so this one is one of the more easy problems. X prime of t is negative a omega sine of omega t. Y prime of t is a omega cosine of omega t, and z prime of t is just b. So x prime of t squared is a squared omega squared sine squared omega t, and y prime of t squared is a squared omega squared cosine of omega t, and z prime of t squared is just b squared. So now x prime of t squared plus y prime of t squared plus z prime of t squared turns out to be a squared omega squared. I'm going to have the sine squared of omega t plus the part from the y prime is going to give me the cosine squared of omega t plus the z part gives me b squared. So I get x prime of t squared plus y prime of t squared plus z prime of t squared turns out to be a squared omega squared plus b squared. So now I can take the square root of both of them. And now I can compute my integral. So now L becomes the integral. I start at 0 and I end at 2 pi over omega. This thing that goes inside here is simply the square root of that. So that term is what goes inside here, because I simplified it very nicely. And that gets integrated dt. So I end up with t times that thing. And then that is evaluated from 0 to 2 pi over omega. So therefore my answer becomes 2 pi over omega times the square root of a squared omega squared plus b squared. And that's the end of that problem. Nice and simple. That's one of the easier ones. Okay. So now what we want to do is we want to define what we call an arc length parameter. So arc length parameter with the base P of T naught. All right, so I'm going to draw this picture. Okay. Again, this is X, this is Y, and this is Z. Okay, so we're going to say that we have some curve that starts we have some curve that's doing something. Okay, so right here, at this point right here, I want to draw a vector. Okay, and that point is P at T naught. And then S of T is the amount of curve that is transverse as T increases. And then, of course, at some point right here, don't necessarily want it to be there. Let's put it right here. This point is R of T. So R of T is following the curve all the way around, okay? And I'm sorry, let me erase this. This hits at the point P of T. R of T is this vector. Okay. So now P of T is simply the point X of T, Y of T, Z of T. So that's some point on the curve. And I'm going to define S of T is the integral from any T naught I start at to T of the length of nu of tau d tau. So here tau is my dummy variable that I'm integrating with respect to. So now I can define S of T to be the integral from T0 to T. And now I'm going to have the square root of X prime of tau squared plus Y prime of tau squared plus Z prime of tau squared d tau. So notice if I tell you this is now a function of T. Okay. So therefore, if I wanted to go back to my last example, what in the world did I call that? Okay, let me go back and call that example. Okay, so now we're going to go back to example 1 and call this example 2. So in example 2, I have a new helix. It is defined by R of T is equal to the cosine of Ti plus the sine of Tj plus Tk. Very simple helix, okay? Then when I go to compute nu of tau, I'm going to get the square root. When I do x prime, I'm going to get the negative sign. I'm going to square it. So that's going to give me sine squared t. When I do sine derivative, I'm going to get cosine. I'm going to square it. So I'm going to get cosine squared t. And when I take t in derivative, I get 1, and I square it, I get 1. Well, lo and behold, this is rather nice. This just comes out to be the square root of 2. So therefore, the arc length at any point where I start and let t naught, so I'm going to let t naught be 0. So the integral from any 0 to t is the integration of nu of tau d tau. So this is just the integral from 0 to t of the square root of 2 d tau. And that just simply becomes the square root for t, the root of 2. All right. So I can now find s of anything. I can find s of t for any t. That is s of pi, s of 2 pi is 2 pi times the square root of 2. S of pi over 2 is equal to pi over 2 times the square root of 2, which equals pi to root of 2, pi over the root of 2. Okay, so I can do that. So that's the arc length. Okay, another example. Example 3 is the distance along a line. So show if u equal to u1i plus u2j plus u3k is a unit vector then the directed distance along the line. Well, let's look at that. How far do we go? So R of t is going to be some x naught where we start plus u1t I. Y of t is going to be y naught plus u2 of t j. And then z of t is going to be z naught plus some u3 of t k. And that's from the point p naught, which is x naught, y naught, z naught. Okay, where t naught equal to 0 is t itself. Okay, so what's new? Well, take the derivative of x, y, and z. So nu of t becomes the square root x prime of t is u1 squared plus u2 squared plus u3 squared, but this thing is a unit vector. So that just equals 1. So therefore, the arc length along a straight line, S of t, the integral from 0 to t of 1 dt. And that's just t. So arc length along the square line is just what it is. Okay. All right, so that's arc length. I love arc length. I think it's beautiful. Okay, so that's arc length. Okay, so now we want to talk about the unit tangent vector. We talked a little bit about this the other day. Okay, so the unit tangent vector. So we're going to talk about this arc length. If you remember arc length S, so we got to remember, it's like you forget real quick. S of t, the integral from t naught to t of nu of tau, d tau. Okay, so we're going to assume that ds dt, which is basically just nu, is positive. So if I do that, so S is a one-to-one decreasing function, increasing function, okay, I should say non-decreasing. It's not, it could be 0. So I'm gonna say non-decreasing. Function. So that very nicely implies that it has an inverse. And its inverse function called dt ds. Okay. So dt ds is 1 over ds dt, but that's just 1 over nu. Okay. Hence, I can talk about now dr ds. So this is a unit vector in the direction of V. All right, so now this is how you define the unit tangent. Okay, the unit tangent vector, it has a special name, it's called T, of a differentiable curve R of T is capital T, and it is dr ds but that's simply just saying dr dt divided by dr dt times dt ds. But that's the same as saying dr dt divided by ds dt. So dr dt we already know is v, and ds dt is nu, but nu is the length of v. So there it is. That's the unit tangent. We talked a little bit about this. So t is a differentiable function of little t whenever v of t is a differentiable function of t. Okay. All right, next example. Find the unit tangent vector of the helix So we're going to use R of t equal cosine of ti plus sine of tj plus tk. So we want to find the unit tangent. Okay, so that means we need to find the unit tangent is r prime of t. Well, it is v of t divided by the length of v of t. But another easy way to think of it is it's r prime of t divided by the length of r prime of t. Okay, so we know r. So r prime is easy to find. R prime of t is negative sine ti plus cosine of tj plus k. That's it. And so the length of r prime of t, well, that's going to be the square root of the sine squared of t plus the cosine squared of t plus 1. We already said that's the square root of 2. Okay. So therefore, t is going to take the vector r prime and divide by the square root of 2. So I'm going to get negative sine of t divided by the square root of 2 I plus the cosine of t divided by the square root of 2 j plus 1 over the square root of 2. Okay, and so there is my unit tangent. Okay. Here's another example. So this is called the involute of a circle. All right, so find the unit tangent vector of the curve. This is a fun curve. R of t is equal to cosine t plus t sine t I plus sine t minus t cosine t j. So now let's compute dr dt. So that's going to be negative sine t plus sine t plus t cosine t I. And then we're going to get cosine t minus cosine t minus t times negative sine t j. Again, here we're assuming t is greater than 0. Okay. All right. So that says that r prime or dr dt turns out to be t cosine t I plus t sine t j. And the length of r prime of t is going to be the square root of t squared cosine squared t plus t squared sine squared t, and that just equals t, because t is positive. Okay. So therefore, the length of V of t is simply just the length of R prime of t, and that's just t. So therefore, the unit tangent vector t is going to be V over its length, and this is V. So that is t cosine t I plus t sine t j divided by t, which is positive. So I just get the cosine of ti plus the sine of tj. So that's the unit tangent. Okay. So now I want to talk about curvature. All right. If t is the unit tangent vector of a smooth curve R of t, then the curvature function is kappa, and kappa is the absolute value it is not. It is the length of dt ds. Okay. Is there another way to write kappa? Kappa is, we know dt, we can find dt divide by dt, yes. Okay, so kappa is, oh, let's find this thing first. So dt ds is to take dt and then multiply by dt ds. But that is dt divided by ds dt. So that is t prime of t divided by df dt, which is the length of v of t. Okay. And this is a vector. So therefore, kappa, the curvature, is to take the length of t prime of t divided by the length of v of t. Okay, let's go back. So let's look at this last example, the involute of the circle. Okay. So for the last example, r of t was cosine t plus t sine ti plus the sine of t minus t cosine tj. And we found r prime of t to be t sine ti new. Why do I feel like it was t cosine t? Because it was. T cosine ti plus t sine tj. And so that, if you remember, is v of t. So the length of v of t turned out to be just t. And so t prime of t is just r prime of t divided by the length of v of t. And then I divide by, so this is just squared. So I think I can do that. Yeah. So as you can see, when I find t prime of t, t of t, and I don't like that yet. I need to figure this out. I gotta remember this. I gotta figure that out. So let's just go back. Got 1 minute. T of t turned out to be cosine ti plus sine tj. Okay, so now we need to find t prime of t. That is minus the sine of t I plus the cosine of tj. And then we have to compute t prime of t divided by the length of v of t. So that is minus sine t over ti plus cosine t over tj. And now we can find kappa. So kappa is the square root of the sine of t over t squared plus the cosine of t over t squared. And that just turns out to be 1 over t. Okay. And we will pick up from here. We will find the normal, the binormal vector, and all that kind of good stuff. Okay, any questions, Inaya? Today was
No.
mostly definitions. Yeah, mostly just definitions. Okay, my dear.